They say the universe is everything there is, everything there was, and everything there ever will be. But here's the catch. The universe we know has an edge, a horizon that limits what we can observe. So, what's beyond that? Is it nothing? Is it more stars, galaxies, or even an entirely new realm of existence? This isn't just a question for astronomers with giant telescopes. This is about the deepest mysteries of existence, ones that challenge our understanding of time, space, and reality itself. Because here's the thing. Beyond that edge, the laws of physics as we know them might not even apply. Let me explain. Imagine standing on a shoreline, staring out at the endless ocean. The horizon looks like the end of the world, but you know there's more water beyond it. That's exactly what the edge of the universe is like, a boundary we can't cross, but one we know hides something bigger, something more profound. Today, we'll explore what could lie beyond this cosmic horizon. Is the universe infinite? Are there parallel universes with different versions of us? Or are we just one tiny bubble in a vast mysterious multiverse? Get ready for a journey that pushes the limits of your imagination and challenges everything you thought you knew about reality. To understand what might lie beyond the edge of the universe, we first need to define what the edge actually is. And here's the twist. It's not really an edge in the way you might imagine. There's no physical boundary, no wall we could hit if we somehow built a spaceship that could travel far enough. Instead, the edge refers to what we call the observable universe, the portion of the cosmos we can see from Earth. Why is it only a portion? It all comes down to light and time. Light travels at a finite speed, about 300,000 kilometers per second. While that's incredibly fast, it still takes time for light from distant objects to reach us. So, when you look at a star 100 light-years away, you're seeing it as it was 100 years ago. Now, scale that up to the age of the universe itself, 13.8 billion years, and you get the observable universe. It's like we're watching a giant cosmic movie, but only the frames that have had time to reach us. And here's where things get even stranger. Based on current cosmological models, the observable universe has a radius of about 46.5 billion light-years today, even though the universe is only about 13.8 billion years old. This discrepancy arises because the universe has been expanding since the Big Bang. This means that the space between objects is stretching out, like dots on a balloon being blown up. So the farthest objects we can see are now much farther away than they were when their light first started its journey to us. Still, this edge isn't the end of space itself, it's just the farthest we can look. It's like standing in the middle of a forest on a foggy day. You can see trees all around you, but beyond a certain point the fog blocks your view. The trees are still there, you just can't see them. But there's another layer to this story. The cosmic event horizon. This is the ultimate limit, the point beyond which light emitted today could never reach us, no matter how long we wait. Think about it. As the universe keeps expanding, some galaxies are moving away from us faster than the speed of light. These galaxies will slip past this event horizon and vanish from view forever. It's a sobering thought. It implies that there is a part of the universe we can see but can never interact with or explore. Conversely, there are regions of the universe that will never see us, no matter how long we wait. In the very distant future, if dark energy continues to dominate, all galaxies outside our local group will move beyond our event horizon, leaving us in an island universe, where we can no longer observe or interact with anything beyond our local group, highlighting the transient nature of our observable universe in the grand scheme of things. So, when we talk about the edge of the universe, we're really talking about limits of light, time, and space itself. But what lies beyond those limits? That's where things get fascinating. But let's take this a step further. What exactly lies beyond the observable universe? We know there's more. The cosmos doesn't just stop at the edge of what we see, much like the forest doesn't end where the fog begins. The light from regions beyond our observational reach simply hasn't had enough time to travel to us. This suggests a staggering reality. The observable universe is only a tiny fraction of the whole universe, a mere drop in an incomprehensibly vast ocean. Now, this isn't just speculation. Observational evidence supports it. When scientists study the cosmic microwave background radiation, the faint afterglow of the Big Bang, they find it to be incredibly uniform. This uniformity implies that the universe extends far beyond what we can observe, continuing in much the same way. Imagine tiling a floor in your house. If the tiles extend well beyond the walls you can see, it's reasonable to assume that the pattern goes on and on, even if you're stuck in one room. But here's where things get mind-bending. If there's more universe out there, possibly an infinite amount, it opens the door to some bizarre consequences. Take infinity, for example. In an infinite universe, there could be infinite galaxies, infinite stars, and even infinite versions of you. Somewhere out there could be a galaxy that looks identical to our Milky Way, with a planet identical to Earth and another you living a slightly different life. Still, there's a catch. If the universe is infinite, why isn't the night sky blindingly bright? This question is called Olber's paradox. If the universe were infinite, static and eternal in every direction we look, our line of sight should eventually hit a star. Each star would contribute light to our night sky. With an infinite number of stars, the sum of their light should make the sky as bright as the surface of a star, regardless of how far away each star is. However, we observe that night sky is mostly dark, with only a finite number of visible stars. The answer lies in the universe's age and its expansion. Because the universe has only existed for 13.8 billion years, there hasn't been enough time for light from all those stars to reach us, explaining the darkness. And because the universe is expanding, some light gets stretched out into longer wavelengths, including into the infrared, becoming invisible to the naked eye. And what about the shape of the universe itself? This is where the concept of curvature comes in. On the larger scales, the universe appears to be flat, like an endless two-dimensional plane. But if you zoom out far enough, could it curve back on itself like the surface of a sphere? If that's the case, then travelling in one direction long enough might eventually bring you back to your starting point. It's a dizzying thought, but one that adds even more complexity to the idea of the universe's edge. Now let's talk about something called the reachable universe. This is the part of the cosmos we could theoretically explore even if we had the technology to travel at the speed of light. But here's the bad news. The reachable universe is much smaller than the observable universe. Why? Because the universe is expanding faster than the speed of light. Think of it like trying to chase a car on a racetrack, while the car keeps accelerating faster than you ever could. No matter how hard you try, you'll never catch up. This expansion doesn't mean galaxies are physically moving through space faster than light. Instead, it's the space between galaxies that's stretching. It's as if you're standing on a rubber band that's being pulled apart, and everything around you is getting farther away, even though nothing is actually moving in the conventional sense. The result? Many galaxies we see today will one day slip beyond the cosmic event horizon and disappear forever. And this isn't just theory, it's already happening. The light we see from certain galaxies is a snapshot from billions of years ago, but those galaxies have since receded so far that their current light will never reach us. This means the universe we observe is a fleeting moment in time, a constantly changing mosaic that's slowly losing pieces as the expansion accelerates. But there's an even deeper implication here. If the universe keeps expanding indefinitely, entire regions of space will become so isolated from one another that they might as well be separate universes. Communication, travel, and even the exchange of energy would become impossible between them. This paints a picture of a fragmented cosmos, where the observable universe is just one small island in an ever-growing sea of disconnected regions. Still, there's a lingering question. If we can't see beyond the observable universe, how can we be so confident that it even exists? The answer lies in indirect evidence. Scientists can analyze patterns in the cosmic microwave background radiation, the large-scale structure of galaxies, and the behavior of dark energy to infer what's likely beyond our horizon. It's a bit like hearing music coming from another room. You might not see the band playing, but you can make some pretty good guesses about what's happening based on the sounds. But let's not overlook the profound philosophical implications of these boundaries. If there's an observable universe, then by definition, there's an unobservable universe as well. Regions we'll never be able to access, no matter how advanced our technology becomes or how far into the future we go. This realization forces us to confront the limits of human knowledge. Could there be phenomena, structures, or entire realms beyond the observable horizon that are so different from anything we know that they defy comprehension? It's not just about what's beyond in terms of distance, it's also about what's beyond in terms of causality. The observable universe represents the area of space with which we can have a cause and effect relationship. For example, the gravitational pull of a distant galaxy cluster can subtly affect how light bends on its way to us. But beyond the observable universe, there's no causal connection. Events that happen there can never influence us, and we can never influence them. It's like living in a bubble. What happens outside the bubble might as well be in another reality. This also raises an unsettling thought. If the universe is infinite or filled with regions forever out of reach, what does that say about our significance? Are we just a minuscule part of an incomprehensibly vast system, one that's indifferent to our existence? Or could there be something deeply meaningful about being aware of the edge itself, about daring to imagine what lies beyond? Perhaps significance doesn't depend on size or scale. The value of our existence may not lie in the vastness we can measure, but in the depth we can create. It's in our consciousness, the remarkable ability to ponder these incomprehensible distances, to search for meaning in the stars, and to reflect deeply on our shared existence. It's in the love we give, the art we create, the questions we ask, and the philosophies we dare to explore. Our significance, then, may not be found in the space we occupy, but in how we fill that space, with meaning, purpose, and connection. This idea resonates with Carl Sagan's cosmic perspective, a humbling yet empowering view of our place in the universe. As he said, there is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. Here's where things take an interesting turn. Some scientists argue that our observable universe might be finite but unbounded. Picture the surface of a sphere. It doesn't have an edge you can fall off, but if you keep travelling in one direction, you'll eventually loop back to where you started. In this scenario, the universe could be shaped in such a way that the concept of beyond becomes irrelevant. There's simply no outside to explore. It's a difficult concept to wrap your head around, but it shows just how much our understanding of space is shaped by our limited perspective. And yet, we're not done questioning. Theories like cosmic inflation suggest that our observable universe could be just one tiny bubble in a vast sea of universes. These bubbles might collide, overlap, or even give rise to one another. If that's the case, the edge of our universe is simply the boundary of our bubble, with countless others floating alongside us in a much larger multiverse. Now let's tie this all together. When we talk about the edge of the universe, what we're really confronting is the limitation of our tools and our perspective. The observable universe is like a stage, and we're watching the performance from our seats. But behind the curtain lies a space we can only imagine, a realm beyond our senses defined by theories and indirect evidence. The fascinating part is that what we consider the edge is constantly changing. As time moves forward, light from more distant regions will have had time to reach us, gradually expanding the observable universe. However, this expansion is a race against the accelerating growth of the cosmos. Some areas will forever remain hidden, slipping beyond our grasp even as others come into view. It's like walking toward the horizon on a treadmill that's moving faster than you. And yet, this constant tug of war between what we can see and what we can't has shaped much of modern cosmology. The discovery of the cosmic microwave background radiation, for example, revealed the faint echoes of the Big Bang, light that had traveled billions of years to reach us. It's a reminder that even though we're confined by our observable bubble, we've managed to decode its secrets with astonishing ingenuity. But here's the most profound question of all. Does the universe even care about what we call its edge? The universe doesn't stop existing because we can't see it. What we call the edge is a human construct, a product of our attempt to make sense of something far larger and more complex than ourselves. It's humbling to realize that, no matter how much we learn, there will always be mysteries that lie just out of reach. So, as we stand on the metaphorical shoreline of the cosmos, staring out at the vast unseeable expanse, we're left with a choice. Do we stop at the horizon and accept its limits, or do we push forward, driven by curiosity and wonder? Because while we may never truly reach the edge of the universe, the journey to understand it will forever expand our perspective and maybe even redefine what it means to explore. Let's imagine for a moment that the universe has no edge, not an observable one, not a physical one, and not even a conceptual one. Instead, it stretches on forever, an infinite expanse with no boundaries, no end. This idea is as overwhelming as it is intriguing. How can we even begin to comprehend infinity? Something so vast defies our imagination. The concept of an infinite universe isn't just a philosophical musing, it's a serious scientific hypothesis supported by evidence. For example, when cosmologists measure the geometry of the universe, they find it to be flat, or very, very close to flat, on the largest scales. A flat universe suggests that it could be infinite, because if it were finite, its curvature would cause it to eventually loop back on itself, like the surface of a sphere. But in a flat universe, you could travel in any direction forever without coming back to where you started. Now, let's pause and unpack what infinity really means in this context. If the universe is infinite, it doesn't just mean more stars and galaxies than we could ever count. It means everything that can happen will happen somewhere an infinite number of times. There could be endless copies of Earth, endless versions of you, and endless versions of this very moment. Somewhere in this infinite expanse, there could be a galaxy identical to our Milky Way, with a planet where another version of you is watching the same video. This isn't just idle speculation, it's a logical consequence of infinity. Think of it like shuffling a deck of cards. If you shuffle long enough, eventually you'll get the same order of cards twice. In an infinite universe, with infinite combinations of matter and energy, every possible arrangement has to occur, not just once, but an infinite number of times. It's a staggering idea, one that makes you question the uniqueness of everything we hold dear. But infinity isn't just a playground for wild speculation. It also comes with challenges. For example, if the universe is infinite in size and uniformly filled with matter, like stars, galaxies, dark matter, then there would be an infinite amount of mass. In classical gravity theory, an infinite amount of mass would imply infinite gravitational force. This would mean that every point in the universe should experience an infinite gravitational pull from all directions, leading to an unstable or paradoxical situation where everything should be crushed together. So, is the universe truly infinite, or does it just appear that way from our limited perspective? That's the question we'll unravel as we dive deeper into the implications of infinity. If the universe is infinite, its implications go far beyond what we can easily grasp. Let's explore one of the most mind-boggling consequences, the possibility of exact replicas. This concept is referred to as infinite monkey theorem, applied to cosmology, where in an infinite universe, given enough space and time, anything that can happen will happen, including exact replicas of Earth with its inhabitants. Imagine travelling so far out into space that you encounter another Earth, a planet with the same continents, the same cities, and the same people. It sounds like science fiction, but in an infinite universe, it's not only possible, it's inevitable. Here's how it works. The universe is comprised of particles arranged in countless combinations. However, the number of ways you can arrange those particles is finite, much like how a deck of cards only has a finite number of possible shuffles. Now, in an infinite universe, those arrangements would eventually repeat, simply because there's unlimited space for them to occur. Somewhere out there, there's an Earth exactly like ours, down to the tiniest detail, and another Earth that's slightly different, maybe where dinosaurs never went extinct or where humans never evolved. This idea is both awe-inspiring and deeply unsettling. It challenges our sense of individuality, of what makes us unique. If there are infinite copies of you, what does it mean to be you? Is your identity tied to this particular version of yourself, or is it shared across countless iterations? It's a question that blends science and philosophy in a way that few other topics can. While this is fascinating to think about, practically these identical replicas would be so far apart that they're beyond our ability to interact with or observe. The distance would be measured in terms of light years or even more, making any encounter with them unimaginable with current technology. But infinity isn't just about doppelgangers and endless repetition. It also raises questions about the future. If the universe is infinite, does that mean time is infinite too? And if so, will everything that's happening now happen again in the distant future? This idea ties to the concept of eternal recurrence, the notion that, given enough time, every possible event will repeat endlessly. This concept was notably explored by Friedrich Nietzsche, who posited that if time is infinite, then every possible configuration of the universe must occur an infinite number of times. Thus, every moment, including this one, would repeat infinitely. If the universe is truly infinite in both space and time, then every possible permutation of matter and some energy would have the chance to repeat. Some cosmological models, like those involving cyclic or oscillating universes, suggest periods of expansion followed by contraction, potentially leading to a big crunch from which a new Big Bang might occur, offering a mechanism for recurrence. Of course, this is all based on the assumption that the universe is not only infinite, but also uniform. If matter and energy are distributed evenly across space, then these patterns and repetitions are a natural consequence. But what if the universe isn't uniform? What if it has vast empty voids or regions so different from ours that the laws of physics themselves don't apply? In that case, infinity becomes even more complex, opening the door to possibilities we can't even begin to imagine. So, while the idea of an infinite universe might seem abstract, its consequences are incredibly personal. It forces us to rethink our place in the cosmos, to question what makes us unique, and to confront the vastness of existence in a way that's both humbling and exhilarating. But let's not forget one of the most practical questions. If the universe is infinite, why can't we prove it? Why don't we have definitive evidence to support this bold claim? The answer lies in the limits of observation. No matter how advanced our telescopes become, they'll always be restricted to observing the finite observable universe, the part of the cosmos whose light has had time to reach us since the Big Bang. What lies beyond this observable limit is uncharted territory, hidden not just by distance, but by time itself. Think about it like this. Imagine standing on a beach and staring out at the ocean. Your eyes can only see as far as the horizon, but you know there's more ocean beyond that. You might even hear the distant roars of waves or catch glimpses of objects floating far away. But without crossing the horizon yourself, you can't confirm exactly what's out there. That's our predicament with the universe. We have hints and mathematical models that suggest infinity, but direct evidence remains elusive. One of the strongest hints comes from the uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation appears almost perfectly consistent no matter which direction we look, suggesting that the universe stretches out in much the same way beyond the limits of our vision. But the word "almost" is key here. Tiny fluctuations in this radiation offer clues about the structure of the universe and hint at possible variations in the infinite expanse. These variations raise another profound question. Even if the universe is infinite, could its infinite regions be wildly different? Imagine one region of the universe where galaxies are densely packed, stars burn brighter, and planets are abundant. Then imagine another region where matter is so sparse that billions of light years pass without a single atom. In an infinite universe, both extremes and everything in between could exist. This doesn't mean that the universe is chaotic, but rather that its vastness allows for every possible variation, even ones we can barely comprehend. Yet even with these hints, proving infinity is an impossible task. No matter how far we travel or how much data we collect, we'll always be confined to a finite perspective. Infinity, by its very nature, is something we can theorize about, but never truly measure. It's like trying to count the grains of sand on a beach. You know the number is vast, but you'll never finish counting to confirm it's truly endless. So what does this mean for our understanding of reality? If we accept the idea of an infinite universe, it forces us to confront some deeply philosophical questions. For instance, can something infinite ever be fully understood? Our brains are wired to think in finite terms, beginnings and endings, boundaries and limits. Infinity defies all of that, presenting a reality so vast that it almost feels beyond human comprehension. And yet, this doesn't stop us from trying. Human curiosity has always been about pushing boundaries, exploring the unknown, and grappling with ideas that challenge our understanding. The concept of an infinite universe is no different. It forces us to rethink not just the cosmos, but our place within it. Is our ability to ponder these questions proof of something extraordinary about our existence? After all, in an infinite universe, we're part of a vast tapestry that's as complex as it is beautiful. Our ability to ask questions, to wonder about what lies beyond, is a uniquely human trait. It's what drives us to explore, to learn, and to push the boundaries of what we know. But let's take this a step further. If the universe is infinite, then every discovery we make is just the beginning. There's no end to our exploration, no final frontier to conquer. Instead, each breakthrough opens the door to even greater mysteries, keeping the quest for knowledge alive forever. Infinity isn't just a concept, it's a challenge, one that inspires us to dream bigger and aim higher. This boundless curiosity is what makes the infinite universe such a powerful idea. It's not just about what's out there, it's about how we interact with it, how it shapes our understanding of reality, and how it fuels our desire to know more. And yet, the idea of infinity isn't without its critics. Some scientists argue that the universe, while vast, may still be finite. They point out that an infinite universe raises paradoxes that are difficult to resolve. For example, if the universe is truly infinite, why does it appear so uniform? Wouldn't we expect to see more variation, more chaos, more extremes? Others suggest that what we perceive as infinity might simply be so large that it feels endless. If the universe is curved in on itself like the surface of a sphere, it could give the illusion of infinity while actually being finite. Imagine an ant crawling on a balloon. From its perspective, the surface seems endless, but we know it's not. Could the universe be playing a similar trick on us? Ultimately, whether the universe is infinite or not, the questions it raises are profoundly humbling. It reminds us of the vastness of existence and the limits of human understanding. But it also sparks something incredible, a sense of wonder, a drive to explore, and a curiosity that refuses to be confined. What if our universe isn't the only one? What if, beyond the edge of the observable universe, there are countless other universes, each with its own unique rules, histories, and possibilities? This is the idea behind the multiverse, a concept that takes the vastness of existence and multiplies it to infinity. Key figures in the development of the multiverse theory include Alan Guth, who worked on the theory of cosmic inflation, proposed the idea of eternal inflation, laying the groundwork for inflationary multiverse. Andre Linde expanded on Guth's work, exploring how quantum fluctuations during inflation could lead to a multiverse with varying physical properties. And Brian Greene, a string theorist. The multiverse theory isn't just a wild idea from science fiction. It has roots in real science, stemming from frameworks like inflationary cosmology, quantum mechanics, and string theory. Let's start with inflationary cosmology. Shortly after the Big Bang, the universe underwent a brief but explosive period of rapid expansion known as inflation. During this time, space stretched so quickly that quantum fluctuations, the tiny random changes in energy, were stretched across vast distances. These fluctuations could have created bubble universes, each forming its own distinct cosmos. Picture a pot of boiling water. As the water heats up, bubbles form, rise, and pop. Now imagine that instead of popping, these bubbles expand indefinitely, each one becoming its own universe with unique physical properties. That's one way to think about the multiverse, a cosmic soup of bubble universes, endlessly forming and growing. Then there's quantum mechanics, which suggests another path to the multiverse. At its core, quantum mechanics is the science of probabilities. When you measure a particle, it doesn't have a single, definite state until you observe it. Before that, it exists in a superposition, meaning it's in all possible states at once. According to the many worlds interpretation of quantum mechanics, every time a quantum event occurs, the universe splits, creating a new branch for every possible outcome. In this view, there are universes where you decided to watch this video and universes where you didn't, an infinite branching tree of possibilities. String theory, another contender in modern physics, adds yet another layer. It proposes that our universe is just one of many that exist in a higher dimensional space. Imagine a loaf of bread with many slices. Each slice represents a universe, and all of these slices coexist within the larger loaf of the multiverse. In this view, the multiverse isn't just about bubbles or branches, it's a multi-dimensional structure where universes can exist side by side. So, what would it mean if the multiverse is real? For one thing, it would redefine our understanding of existence. Instead of being a singular entity, the universe would be one of countless realities, each with its own unique set of physical laws and initial conditions. Some universes might resemble ours, with galaxies, stars, and planets. Others might be unrecognizable, governed by forces and particles that don't exist in our universe. This also raises questions about the nature of life. In a multiverse, the conditions for life could vary dramatically from one universe to another. There could be universes where life is abundant, flourishing in countless forms across countless worlds, and there could be universes where life is impossible, where the laws of physics prevent atoms from forming or stars from shining. But the multiverse doesn't just challenge our understanding of physics, it challenges our understanding of ourselves. If there are infinite universes, does that mean there are infinite versions of you? In one universe, you might be a scientist discovering the secrets of the cosmos. In another, you might be an artist, a musician, or even someone who never existed at all. The multiverse makes identity fluid, a kaleidoscope of possibilities that stretches far beyond our current understanding. Of course, these ideas come with their fair share of skepticism. Critics argue that the multiverse theory is untestable, meaning it's impossible to gather evidence to prove or disprove it. After all, if these other universes exist beyond our observable horizon, how could we ever hope to detect them? Proponents counter that while we might not be able to observe other universes directly, we can look for indirect evidence. For instance, the patterns in the cosmic microwave background radiation, or the properties of dark energy, could offer clues about the existence of other universes. Despite the controversy, the multiverse remains a tantalizing idea. It's a concept that pushes the boundaries of science and philosophy, inventing us to imagine a reality far larger and more complex than we ever thought possible. Let's zoom in on one of the most fascinating aspects of the multiverse: the idea that some universes might overlap or even collide with ours. In inflationary cosmology, the bubbles that represent different universes could occasionally bump into each other. If that happens, the collision could leave behind observable traces, ripples in the cosmic microwave background, or distortions in the distribution of galaxies. Scientists have even searched for these signs, though so far no conclusive evidence has been found. But what if universes don't just collide? What if they interact in more subtle ways? Some theories suggest that gravity, the weakest of the fundamental forces, might be able to leak between universes. This could explain why gravity is so much weaker than the other forces. It's spread out across multiple dimensions, diluting its strength in our own universe. If this is true, it could open the door to entirely new ways of exploring the multiverse. There's also the question of what it would mean to communicate with another universe. Could advanced civilizations in parallel realities find a way to reach us? Or could we one day develop the technology to send signals beyond our bubble? These ideas sound like science fiction, but they're rooted in genuine scientific curiosity. After all, the multiverse isn't just about what's there, it's about how it might connect to us. The multiverse also forces us to confront deep philosophical questions. If there are infinite universes, what does that mean for the concept of free will? Every decision you make could create a new branch in the multiverse, one where you choose differently. In that sense, every choice you didn't make still exists, just in another universe. Does this mean that all possibilities are predetermined, playing out in parallel? Or does it mean that choice itself is an illusion, with every outcome already accounted for? Then there's the question of meaning. If the multiverse is infinite, does it diminish the significance of our universe, or of our lives? Some argue that it does. After all, if there are infinite versions of us, how can any one version truly matter? But others take the opposite view. They argue that the multiverse makes existence even more meaningful, because it shows how rare and precious it is to experience this specific version of reality. These philosophical debates remind us that the multiverse isn't just a scientific idea. It's a lens through which we can explore some of the deepest questions about our existence, purpose, and identity. It challenges us to think beyond the boundaries of our universe and to imagine what might lie beyond the edge of reality itself. In the end, the multiverse is as much a question as it is a theory. It asks us to rethink everything we know about the cosmos, to imagine possibilities that go far beyond our observable universe. Whether it's infinite bubbles, branching timelines, or higher dimensional slices, the multiverse expands our understanding of what's possible and what it means to exist. But perhaps the most exciting thing about the multiverse is how little we truly know about it. Every new discovery in physics, cosmology, and quantum mechanics brings us closer to answering these questions, but it also opens up new mysteries to explore. The multiverse isn't just a scientific concept, it's a journey, one that takes us to the very edge of human understanding and invites us to dream of what lies beyond. For now, the multiverse remains a theory, a tantalizing possibility that challenges the limits of what we can observe and understand. But even as a theory, it's a powerful reminder of just how vast, complex, and mysterious the universe truly is. Imagine a cold universe where there are no stars, no light and no life, just an endless expanse of darkness and cold. This is the unsettling premise of the dead universe theory, a concept that suggests our observable universe might be a small fragment of a much older, larger universe that has already run its course. According to this theory, our universe could have emerged from the remains of this predecessor, a cosmic phoenix born from the ashes of a dead cosmos. The dead universe theory is rooted in the idea that the universe goes through cycles of creation and destruction. Think of it like the seasons. Just as spring follows winter, the death of one universe could pave the way for the birth of another. This process might involve massive collapses known as big crunches, where the universe contracts under its own gravity, shrinking back to a singularity before exploding outward again in another big bang. In this view, the remnants of the previous universe, its dark matter, dark energy, and even black holes might still be present in ours. These relics could shape the structure of our cosmos, influencing everything from the formation of galaxies to the behavior of gravity. It's as if the past universe left behind a blueprint, one that continues to guide the evolution of the current one. But why would a universe die in the first place? The answer lies in entropy. According to the second law of thermodynamics, entropy, the measure of disorder in a system, always increases over time. In a closed system like the universe, this means that energy becomes more spread out and less useful as time goes on. Stars burn out, galaxies drift apart, and eventually the universe reaches a state of maximum entropy, where no energy remains to fuel processes like star formation. What's left is a cold, dark, and lifeless expanse, the very definition of a dead universe. So, what evidence might support the idea of a dead universe? One clue lies in the mysterious nature of dark matter and dark energy. Dark matter makes up about 27% of the universe, yet it's invisible and interacts with normal matter only through gravity. Some scientists like Roger Penrose proposed the conformal cyclic cosmology theory, where each universe undergoes cycles of expansion and contraction. In this theory, dark matter could be a remnant or scar from previous aeons of the universe. Though not directly linking dark matter to a previous universe in the conventional sense, his work provides a framework where such ideas could fit. Dark energy, which accounts for roughly 68% of the universe, presents another intriguing possibility. This enigmatic force is driving the accelerated expansion of the universe, pushing galaxies farther and farther apart. Could dark energy be the fading echo of a prior universe's energy field, slowly dissipating as our cosmos expands into its final state? If so, it might provide a link between the death of one universe and the birth of another. The idea of a dead universe also aligns with certain cyclic models of cosmology. For instance, the ekpyrotic model, proposed by physicists Paul Steinhardt and Neil Turok, suggests that the universe undergoes an eternal cycle of big bangs and big crunches. In this scenario, our current universe is just one in an infinite sequence, each born from the collapse of the previous. This model suggests a universe where time doesn't have a clear beginning or end, but is instead a repeating sequence. Imagine a pendulum swinging back and forth, with each swing representing the birth and death of a universe. It's a compelling vision, one that challenges the idea of a single linear timeline and replaces it with an endless loop. But there's another darker possibility to consider. What if our universe isn't part of an eternal cycle? What if it's heading toward its own inevitable death, with no rebirth to follow? This is the concept of heat death, a scenario where the universe continues to expand until all energy is evenly distributed, leaving nothing but a uniform, featureless void. In this case, the dead universe wouldn't be a precursor to something new. It would be the final chapter in the cosmic story. One of the most haunting aspects of the dead universe theory is the role of black holes. These cosmic behemoths formed from the remnants of massive stars could hold the key to understanding the death of the universe. Over time, black holes slowly evaporate through a process called Hawking radiation, emitting tiny amounts of energy as they shrink. In a dead universe where all other forms of matter and energy have dissipated, black holes could be the last remaining structures, slowly fading away into nothingness. But what if black holes are more than just remnants? Some theorists propose that black holes could serve as bridges between universes. John Archibald Wheeler, who coined the term black hole, significantly contributed to our understanding of these cosmic phenomena. He explored the concept of wormholes, hypothetical tunnels through space-time, and speculated about the possibility of black holes connecting to other regions of space-time or even other universes. Nikodem Poplovsky extended this bold vision, proposing that the interior of every black hole could be the beginning of another universe, suggesting that our universe might be inside a black hole in a higher dimension of space. In this scenario, black holes could indeed act as portals or birthplaces for new universes. When a black hole collapses into a singularity, a point of infinite density, it creates conditions similar to those of the Big Bang. Could this process spawn a new universe, one hidden from ours but existing as part of a larger multiverse? If so, the death of a universe might not be the end, but a transformation, a seed for new beginnings. There's also the intriguing possibility of white holes, theoretical phenomenon that are essentially the reverse of black holes. While black holes pull matter in and trap it forever, white holes would expel matter and energy, never allowing anything to enter. Some scientists speculate that our universe might have emerged from a white hole formed during the collapse of a prior universe. If true, this would mean the dead universe isn't just a grim concept. It's an integral part of the cycle of cosmic renewal. And yet, the evidence for these ideas remains elusive. Black holes are notoriously difficult to study, and white holes, if they exist, have never been observed. But the questions they raise are profound, forcing us to consider the possibility that the end of one universe might be the beginning of another, a cycle that stretches back infinitely and will continue infinitely into the future. Beyond the scientific implications, the dead universe theory has profound philosophical consequences. If universes are born and die in cycles, what does that say about the nature of time? Is time itself infinite, or does it reset with each new universe? And what about meaning? If the universe we know is just one in an endless series, does that diminish its significance, or does it make it even more extraordinary? One perspective is that the dead universe theory highlights the resilience of existence. Even in the face of entropy and decay, the cosmos finds a way to renew itself, creating new opportunities for stars to shine, planets to form, and life to emerge. It's a vision of hope, one that suggests the universe is a dynamic, ever-changing system rather than a static one-time event. On the other hand, the idea of an infinite cycle can be unsettling. If universes come and go without end, does that mean history is doomed to repeat itself? Are we living in a cosmic loop where every event, every life, and every moment has played out countless times before? Or is each cycle unique with its own distinct story to tell? These questions push the boundaries of both science and philosophy, inviting us to think deeply about the nature of existence itself. Ultimately, the dead universe theory forces us to confront the fragility of our cosmos. It reminds us that, no matter how vast and eternal the universe might seem, it is subject to the same laws of physics that govern everything else. Stars will die, galaxies will drift apart, and one day the universe as we know it will end. But whether that end is final or part of a larger cycle remains one of the great mysteries of cosmology. For now, the dead universe theory remains just that, a theory, but it offers a glimpse of the incredible complexity of the cosmos, showing us that even in the face of death, there is the potential for renewal. It challenges us to rethink our place in the universe, to embrace the fleeting beauty of existence, and to marvel at the possibility that even the darkest, coldest reaches of space might hold the seeds of something new. If you've ever stared at the night sky and wondered if someone out there might be staring back, you're not alone. The search for extraterrestrial life has captivated human imagination for centuries, and as our understanding of the universe grows, so does the possibility that advanced civilizations might exist, not just within our observable universe, but far beyond its edge. Think about this. The observable universe contains billions of galaxies, each home to billions of stars. Even if intelligent life is incredibly rare, the sheer number of stars and planets means it's almost statistically certain that we're not the only intelligent beings out there. Now, expand that idea to what might lie beyond the observable universe, regions of space we can't see or reach. If civilizations exist there, their level of advancement might surpass anything we can comprehend. But here's where things get even more fascinating. According to the Kardashev scale, a system for measuring the technological advancements of civilizations, there are three main types. Type 1, which harness the energy of an entire planet. Type 2, which uses the energy of a star. And Type 3, which controls the energy of an entire galaxy. Humanity, by comparison, isn't even at Type 1 yet. If advanced civilizations beyond our observable universe have had billions or even trillions of years more to evolve, they could be far beyond Type 3, potentially manipulating the fabric of space and time itself. This raises some intriguing possibilities. Could these civilizations have found ways to bypass the limits of the observable universe? Could they travel faster than the speed of light, cross vast distances in an instant, or even exist in multiple universes simultaneously? If so, they might have insights into the nature of the universe or multiverse that we can only dream of. And yet, despite their advanced capabilities, we have no evidence of their existence. Why is that? This question brings us to the famous Fermi paradox, which asks, if intelligent life is so likely, why haven't we seen any evidence of it? One possible answer is that these advanced civilizations are simply too far away, beyond the edge of our observable universe. Light from their galaxies might not have had time to reach us, or their signals might have dissipated over billions of years. In essence, they're hidden from us by the same limits that define the observable universe. But there's another possibility. They don't want to be found. If a civilization reaches an advanced stage, it might choose to remain hidden, avoiding contact with less developed civilizations like ours. Think about it from their perspective. If we stumbled on a planet filled with ants, would we try to communicate with them? Maybe, but it's more likely that we'd observe from a distance, curious but uninvolved. Advanced civilizations might view us in the same way, not as equals, but as curiosities. Alternatively, they might have transcended physical existence altogether. Some theories suggest that advanced civilizations could abandon their physical forms and exist as pure energy or information spread across the cosmos in ways we can't even begin to comprehend. In his book Cosmos, Carl Sagan discusses how life might evolve beyond physical constraints, potentially into forms where intelligence moves to non-biological substrates. In this case, they wouldn't leave behind the kind of evidence we're looking for. no radio signals, no Dyson spheres, nothing we'd recognize as a sign of life. And then there's the idea that we're simply looking in the wrong way. Our search for extraterrestrial life is based on our own assumptions about what life looks like and how it communicates. But life beyond the observable universe might be fundamentally different from anything we've ever imagined. It might use technologies or languages that are completely alien to us, making it effectively invisible to our current methods of detection. But let's entertain a more radical idea. What if these advanced civilizations have already found us? If they've developed the ability to traverse vast cosmic distances or extend beyond the limits of space-time, they might already be here, observing us without our knowledge. This idea connects to the zoo hypothesis, which suggests that advanced civilizations might deliberately avoid interfering with less advanced ones, much like zookeepers observe animals without disrupting their natural behavior. Imagine a civilization so advanced that it could manipulate space-time itself, creating portals or wormholes to move across the multiverse. To us, their technology would seem indistinguishable from magic, a phrase famously coined by science fiction writer Arthur C. Clarke. They might use these abilities to observe or study us, leaving no trace of their presence. Another possibility is that these civilizations could be actively shaping the universe around us in ways we don't yet understand. For instance, they might be using dark matter to manipulate the expansion of the universe, or harnessing black holes as sources of power. If so, we might be seeing the effects of their actions without realizing it, like noticing ripples on a pond without knowing what caused them. But why would they do this? One explanation is that advanced civilizations might have goals or motivations that are completely alien to us. While we're focused on survival, exploration, and technological progress, they might be pursuing objectives we can't even conceptualize. Perhaps they're moved beyond the need for physical resources, focusing instead on mastering the underlying laws of the universe, or creating entirely new ones. Of course, the idea of advanced civilizations beyond the edge of the universe raises profound philosophical questions. If such beings exist, what does that mean for humanity's place in the cosmos? Are we a small, insignificant part of a vast system, or are we uniquely significant because of our curiosity and ability to wonder? There's also the question of morality. If advanced civilizations have had billions of years to develop, how might their ethical frameworks differ from ours? Would they see us as equals, as children to be guided, or as irrelevant specks in an infinite cosmos? And what would it mean for us to encounter them? Would it unite humanity under a common purpose, or would it cause existential panic, forcing us to confront the vastness of the universe and our small role within it? These questions aren't just theoretical, they're deeply personal. They challenge us to think about what it means to be human, to explore the unknown, and to seek connection in a universe that might be teeming with life or utterly silent. But even if we never find evidence of advanced civilizations, the very act of searching changes us. It pushes us to develop new technologies, ask new questions, and expand our understanding of the universe. In a way, the search itself is a form of progress, a reflection of humanity's boundless curiosity and desire to explore. So, what can we take away from the idea of advanced civilizations beyond the edge of the universe? For one, it's a reminder of the incredible scale and complexity of the cosmos. Whether or not these civilizations exist, the fact that we can even imagine them speaks to the power of human curiosity and imagination. It's also a humbling thought. If advanced beings are out there, they might see us as a young, developing civilization, one that still has much to learn about the universe and itself. But that's not a bad thing. Every great journey starts with a single step, and in the grand scheme of the cosmos, humanity is just beginning its journey. Perhaps the most important lesson is that the search for life, whether it's within our universes or beyond, reminds us of our shared humanity. It encourages us to look beyond our differences, to see ourselves as part of something larger, and to work together to explore the unknown. When you think about the edge of the universe, it's natural to wonder what might exist in those farthest reaches. Could there be unique planets, edge planets, that sit on the extreme limits of the cosmos, so distant that they defy our current understanding of space and time? This idea sparks not just curiosity, but also profound questions about how the universe itself is shaped. To understand edge planets, we first need to revisit the concept of the universe's shape. Observations suggest that, on a larger scale, the universe appears to be flat. This doesn't mean it's two-dimensional, rather it means that parallel lines would never meet, and light travels in straight paths. However, if space-time has a curvature, as many theories propose, then the universe might not be infinite, but instead finite and unbounded, like the surface of a sphere. In such a universe, travelling in one direction indefinitely would eventually bring you back to your starting point. Now, imagine this curved space-time. If there were planets located at the edges of this curvature, regions where space-time bends the most, they would exist in unique environments, unlike anything we've seen before. These edge planets might experience gravitational forces so extreme that time itself flows differently. Days and years could stretch or shrink, creating bizarre rhythms of life or preventing life altogether. But could we ever detect such planets? The answer lies in light and its interaction with curved space-time. If these edge planets exist, the light they emit might follow strange looping paths due to the curvature of space. This could make them appear in multiple locations at once or distort their images into unrecognizable shapes. It's a phenomenon known as gravitational lensing, and while we've observed it on smaller scales, detecting it on the scale of the entire universe remains a challenge. But edge planets aren't just about gravitational oddities. They also offer glimpses into the boundaries of the universe itself. If the cosmos is finite, then these planets might sit at the farthest reaches of space, marking the limits of what we can observe. Imagine standing on an edge planet, looking out into the void beyond. What would you see? Would it be pure darkness, an endless stretch of nothingness? Or would it be something else entirely, evidence of a multiverse, a higher dimension, or the remnants of another universe? These edge planets might also serve as natural laboratories for understanding the fundamental laws of physics. In the extreme environments of the universe's outermost regions, the behavior of matter and energy could differ dramatically from what we observe closer to home. For example, dark matter, the mysterious substance that makes up most of the universe's mass, might interact more visibly in these regions, offering clues about its nature. Similarly, the effects of dark energy which drives the universe's expansion might be more pronounced near these edges, giving us a chance to study its properties up close. The existence of edge planets also raises questions about habitability. Could life exist in such extreme environments? On Earth, we've discovered life in some of the harshest conditions imaginable: deep ocean trenches, volcanic vents, even radioactive wastelands. This suggests that life might be more adaptable than we think. If edge planets have stable climates, liquid water, or sources of energy, they could host forms of life that are radically different from anything we've ever seen. But what if these edge planets don't actually exist? What if the universe is infinite, with no edges or boundaries to speak of? In this case, the concept of an edge planet becomes a thought experiment, a way to probe the limits of our understanding. Even so, the idea still holds value. It forces us to think about how the universe is structured and how far we're willing to go to explore it. For instance, some theories suggest that the observable universe is just a small bubble within a much larger multiverse. In this scenario, the edges we perceive might not be edges at all, but rather the boundaries of our bubble. Edge planets, then, would be the last outposts before crossing into the unknown, a place where one universe ends and another begins. This idea aligns with the concept of cosmic horizons. Beyond a certain point, the expansion of the universe becomes so rapid that light from distant objects can never reach us. If edge planets exist near this horizon, they would be forever out of reach, tantalizingly close, yet impossible to explore. Their light might take billions of years to travel to us, only to be stretched into oblivion by the expansion of space. It's a sobering reminder of the limits of observation and the vastness of the cosmos. Philosophically, the concept of edge planets challenges our understanding of boundaries. We're used to thinking in terms of edges, land meets sea, night meets day, beginnings meet endings. But the universe doesn't follow the same rules. Its edges, if they exist, might be more like transitions than hard boundaries. They could represent shifts in the laws of physics, changes in dimensionality, or even portals to entirely new realities. This idea has profound implications for how we view our place in the cosmos. If edge planets exist, they might serve as a bridge between the known and the unknown, a place where the rules we take for granted begin to break down. For explorers and scientists, these planets would be the ultimate frontier, a destination that represents the culmination of human curiosity and ingenuity. But the concept of edge planets also forces us to confront our limitations. Even with the most advanced technology, reaching the farthest corners of the universe might be impossible. The distances are simply too vast, the obstacles too great. Yet this doesn't diminish the importance of imagining what might lie out there. It's the act of asking these questions, of pushing the boundaries of our understanding, that drives progress and fuels discovery. In the end, the idea of edge planets is as much about exploration as it is about the unknown. Whether they exist as real worlds or as theoretical constructs, they remind us of the incredible complexity of the universe and the endless possibilities it holds. They challenge us to look beyond our horizons, to imagine what might lie at the farthest reaches of existence, and to embrace the mysteries that make the cosmos so endlessly fascinating. Edge planets might never be directly observed, and their existence might remain a topic of debate, but their value lies in the questions they inspire, the what-ifs that push us to explore the nature of reality itself. They're a reminder that even at the edge of the universe, there's always more to discover, more to understand, and more to imagine. The universe is vast, mysterious, and overwhelmingly complex. And yet, no matter how much we learn, we're always confronted with one undeniable truth. Our understanding has limits. These boundaries aren't just technical, they're deeply rooted in the nature of the cosmos itself and the limitations of human perception. Let's start with the most obvious limitation: our tools. Telescopes, satellites, and particle accelerators have allowed us to glimpse the vastness of space and the inner workings of matter. But these tools can only go so far. Even the most powerful telescopes, like the James Webb Space Telescope, are limited to observing the unobservable universe, what we can see based on the light that's had time to reach us. Beyond this horizon lies an uncharted expanse that's not only out of sight, but also potentially out of reach forever. And then there's the challenge of scale. The universe operates on extremes: galaxies that span hundreds of thousands of light years, particles so small they defy direct observation, and forces that govern the very fabric of space-time. Our understanding is stuck somewhere in the middle, rooted in human-sized perspectives. While we've developed models to bridge these extremes, like quantum mechanics for the very small and general relativity for the very large, these frameworks don't always agree with one another. At some point, our models break down, leaving us with gaps that no current theory can fill. One of the biggest mysteries we face is dark matter and dark energy. Together, they make up about 95% of the universe's total mass and energy. Yet we don't know what they are. Dark matter doesn't emit or absorb light, making it invisible to our instruments, while dark energy remains an enigmatic force driving the accelerated expansion of the universe. These unknowns aren't just gaps in our knowledge. They're fundamental to understanding how the universe works. Without them, our current models of cosmology fall apart. This brings us to another limitation: the nature of observation itself. At the quantum level, particles don't behave in predictable ways until they're observed, a phenomenon famously demonstrated in the double-slit experiment. This suggests that the act of observation changes reality in some fundamental way. If this principle applies on larger scales, then our attempts to understand the universe might always be influenced by our methods of observation, creating a kind of cosmic feedback loop where the more we try to understand, the more elusive the truth becomes. Another obstacle is the nature of space-time itself. The further we look into the universe, the farther back in time we see. Since light takes time to travel across vast distances, this means our view of the cosmos is always a snapshot of the past, not the present. It's like trying to understand a person's life by looking at a single photograph from decades ago. While we can infer certain details, the full picture remains out of reach, hidden by the relentless passage of time. But it's not just physical limitations that constrain us. It's also cognitive ones. As humans, we're bound by the way our brains process information. We evolved to understand the world on a practical scale: how to find food, navigate terrain, and interact with others. Concepts like infinity, higher dimensions, and quantum mechanics are so far removed from our everyday experience that they challenge the very limits of human comprehension. Take higher dimensions, for example. While we live in a three-dimensional world, theories like string theory suggest there could be as many as 11 dimensions. But what would that even look like? Our brains are wired to think in terms of length, width, and height. Trying to visualize a fourth spatial dimension, or a fifth or a sixth, is like trying to imagine a color we've never seen. We can describe it mathematically, but truly understanding it is another matter entirely. This cognitive gap isn't necessarily a flaw, it's simply a reflection of our evolutionary history. But it does mean that there may be aspects of the universe that are fundamentally beyond our grasp. Concepts that we'll never fully understand because our brains aren't equipped to process them. It's a humbling thought, but it also underscores the importance of collaboration. By pooling our collective knowledge and perspectives, we can overcome some of these individual limitations and push the boundaries of what we know. Another limitation we face is time. The universe is about 13.8 billion years old, and its story is still unfolding. But humanity has only existed for a tiny fraction of that time, roughly 200,000 years ago, based on archaeological and genetic evidence. Our scientific revolution began just a few centuries ago, and much of our progress has been made in the last 100 years. In cosmic terms, we're like infants, just beginning to explore our surroundings. This raises an intriguing question. What will future generations know that we don't? If humanity survives for another 1,000, 10,000, or even 1,000,000 years, how much more advanced will our understanding become? Will we solve the mysteries of the dark matter and dark energy? Will we develop technologies to observe beyond the cosmic horizon? Or will we discover entirely new phenomena that reshape our understanding of reality? But time is also a limiting factor in another sense. Some processes in the universe occur on scales far beyond human lifetimes. For example, the life cycle of stars takes millions to billions of years, making it impossible for us to observe the full process directly. Instead, we rely on snapshots from different stages of stellar evolution to piece together the bigger picture. While this approach has been remarkably successful, it also means that some aspects of the universe will always remain partially hidden, revealed only in fragments. Ultimately, the limitations of our understanding are both a challenge and an opportunity. They remind us of how much we still have to learn, but they also inspire us to keep pushing the boundaries of what's possible. After all, every breakthrough in science, from the discovery of gravity to the mapping of the human genome, began with the recognition of a gap in our knowledge. These limitations also force us to confront the fundamental mystery of existence. Why is there something rather than nothing? What is the universe made of, and why does it behave the way it does? These aren't just scientific questions, they're existential ones, tied to our deepest sense of wonder and curiosity. And perhaps that's the most important takeaway. The universe may always remain partly mysterious, its secrets hidden behind cosmic horizons and cognitive limits. But the act of searching, of asking questions and seeking answers is what makes us human. It's what drives progress, fuels innovation, and connects us to the vastness of the cosmos. So, while our understanding may always have limits, our curiosity does not. And as long as we continue to ask why and what if, we'll keep discovering new ways to understand the universe and ourselves. Moving on, the vastness of the universe also forces us to rethink our definitions of community and connection. On Earth, we often define ourselves by our nations, cultures, and beliefs. But when we look at the universe as a whole, these divisions seem trivial. From the perspective of the cosmos, humanity is one species, united by a shared curiosity and a shared density. The universe reminds us that we're all part of the same story, a story that spans billions of years and countless light years. Ultimately, the philosophical implications of the universe are as profound as its scientific mysteries. They force us to confront the unknown, to question our assumptions, and to grapple with the biggest questions of all. Who are we? Why are we here? And what is our place in the cosmos? These questions might never have definitive answers, but that doesn't diminish their importance. In fact, it's the act of asking these questions that makes them meaningful. They push us to explore, to imagine, and to connect with something larger than ourselves. They remind us that even in the face of infinity, we have the power to seek understanding, to create meaning, and to leave our mark on the universe. And perhaps that's the greatest lesson of all. The universe is vast, mysterious, and endlessly complex. But it's also a mirror, a reflection of our own curiosity, creativity, and drive to explore. It challenges us to dream big, to embrace the unknown, and to find beauty in the journey, even when the destination is uncertain. In the end, the universe isn't just something we observe, it's something we're part of. And as long as we continue to ask questions, to seek answers, and to wonder what lies beyond, we'll remain connected to the cosmos in ways that are both profound and deeply human.